Hi everyone, welcome to an intro video on derivatives. The focus of this video is on the interpretation of the derivative. Visually, we can define a derivative as a type of sensitivity of a function to small changes in the x value. So how much does the y value change for a given change in the x coordinate? You can imagine sitting on this curve, let's say up here, and adding a little tiny bit to the x value. Let's say adding 0.1 to the x value and then seeing how much does the y value change if I do that. Then doing the same thing down here. So starting at that first purple dot, one on the bottom left, and then adding that same 0.1 to the x coordinate and seeing how much does the y value change at that point. And you'd find that at the bottom left, that point, the function is more sensitive to changes in the x coordinate. The y value changes by more for a given change in the x value. This sensitivity is connected to another geometric property called the tangent line of the function at a point. The tangent line is the line that just barely touches the function at a point, and that line is one that could be used as the best linear approximation of that function at that point. The tangent line for the curve at the top of the hill is shown in red. It's a horizontal line. The slope of that line, like all horizontal lines, is 0. The function is also not very sensitive to changes in the x-coordinate there. It's rather insensitive, actually. But as you move to the right, or you move to the left, but in the picture I'm showing moving to the right, the tangent line becomes steep. It's no longer 0. It's now tilted down with some non-zero slope. The function also becomes more sensitive to changes in the y value. Moving further to the right, you get to an even steeper part of the curve and a greater sensitivity of changes to the y value on small changes to the x value. So there is a direct connection between this sensitivity of the function and the slope of the tangent line at that point. How do we make it precise? Since we're talking about slopes of tangent lines, and we're trying to connect that to sensitivities, we need a definition that resembles slope. This is not going to be the end of the story. I'm going to give you a formula for the definition of the derivative at a point, and I want to go back and motivate a little bit more. But it is important, I think, to at least throw the formula in here to give you an idea of what is our goal when we talk about derivatives. So the following definition is for the derivative of a function f at x equals a. The notation for the derivative is f prime. If we're looking at for the derivative at a, it's f prime at a, and it's equal to a limit. The limit as h approaches 0 of the following quantity: f of a plus h minus f of a all divided by h. The top part, f of a plus h, that's plugging something into a function. F of a is plugging something into a function as well. We're subtracting them. Well, plugging something into a function gives you a y value. We have a y value minus a y value. That's a delta y. H actually is a delta x. It's how much we are changing the input into the function by. Notice that the first input is a plus h. The second input is a. The difference between them is h. So what this is the limit of a delta y over a delta x. This is the limit of a slope, a very special slope. If this limit exists, it is said that the function has a derivative at a, and the value of the derivative at a is equal to the value of that limit. I want to get to this point with a little bit more motivation. So, good news story, your future company bank account. On the x-axis, going left and right, would be your years in operation. On the y-axis would be how much money is in the company's bank account. So you start with nothing, 0. At 0 years, you have $0. Maybe the y-axis is millions of dollars, but it's still 0 millions of dollars. Notice that as time goes on, the bank account's increasing. And it never dips down. Like, this is a really good news story. By the end of year 10, you have $20 or $20 million or $20 billion, whatever it is, whatever the units are, it doesn't matter. You have more than what you started with. And you never went down at any point in between. The bank account just kept increasing. So congrats. Good work. But looking at that picture, you obviously had some years that were better than other years. Like at what years did it look like your bank account grew more quickly? Well, it looked like it was growing pretty good there and here. And then things slowed down here. Well, I want to quantify these things. How quickly was it changing in a particular set of years? Like how much did it change by from year 2 to year 4? Where did it slow down the most? Where was the growth rate the slowest? So the growth rate slowest around here somewhere. We can quantify these things using fairly simple math. I'm going to define the growth rate as how much the y value changes divided by how much the x value changes. The slope, delta y over delta x. So the first question I want to ask you is, what was your average growth rate over 10 years? So this is a fairly easy question to answer. Your average growth rate is how much did you grow by from year 10 to from year 0 to year 10. You grew 20 million minus 0 million, so $20 million. And how many years were elapsed? So divide by the number of years, 10 minus 0, so 10. So 20 divided by 10. On average, you added $2 million per year. Now go back and think about that. On average, you add $2 million per year for 10 years, you're going to have $20 million. So that's just how averages work. It's all sensible. So plug in your numbers, y of 10 minus y of 0 over 10 minus 0, your delta y over delta x, 20 over 10 equals 2. So again, that's just the average over the full 10-year period. What if we wanted to ask, were the first 5 years better or worse than the second set of 5 years? Were we better off from year 0 to year 5, or was our growth rate higher from year 5 to year 10? We can answer that question in part by calculating the average growth rate from year 0 to year 5. So doing the same thing, using a delta y over delta x, so that at year 5 our bank account was at 12 million. So that would be our y ending point. So 12 minus 0 divided by 5 minus 0. 12 divided by 5, which is 2.4. How do you do that, by the way? How do you do that without a calculator? 12 over 5 equals 12 over 5. I'm going to multiply top and bottom by 2. Times 2 over 2. Multiplying by 1, which means not changing the answer. So 24 over 10. And it's easy to divide by 10. We just shift the decimal place over by 1, which is 2.4. So that's one trick for dealing with fractions and trying to get them into decimals. And there's other tricks. I'll erase that now, since I don't want you to panic about that and think that's something that you have to do. We don't have decimals in the course. Now, let's compare that. That was $2.4 million average per year over the first 5 years. We're comparing that to the 2. It's higher. So the first 5 years were definitely better than the next set of 5 years. Let's graph the lines that connect those points together. The line that connects the beginning at year 0 to the end at year 10 is shown in green. The line that connects year 0 to year 5 is shown in blue. It shifted for some reason. Doesn't matter. I'm going to put them together. What do you see? You see the blue line has a higher slope than the green line. The delta y over delta x is larger. When we calculate slopes of lines, we're just, in a sense, it's a measure of average. If we're calculating the slope as a delta y over delta x, in the way that we've been doing. Slope of line connecting those points. Now, we could do the same thing at different points of time. We could say, what was the average growth rate from year 4 to year 8? Or from year 2 to year 5? Or from year 8 to year 10? We could look at different windows and look at the average growth rate in all those different windows and make a statement, like what 2 years were our best, which 2 years were our worst. You might be able to do that by looking at the picture. I also want to be able to ask, which week was the best? Which minute was the best? I can't do that with a graph like this. The graph isn't high enough quality, but if we're talking about functions, and functions that have a domain over all the real numbers, then we certainly do have enough granularity. We have enough detail to answer that question about what's happening over any instant. So you can imagine taking these lines and shrinking them down. I don't know if I can still zoom. Yeah, it's letting me zoom in. So if you were to zoom in at one of these points, let's say go from here to here, and draw the line that's connecting them, but zoom in even closer than that, go from here to here and connect them. What you begin constructing is you begin constructing a tangent line. The line's barely touching the curve at the point. You're constructing that idea of the sensitivity of the graph to a small change in the x value. What you create is on the right hand side, it's showing you the tangent line, the sensitivity of the graph at different points as we move along the x-axis. At places where the curve is very steep, the slope of the tangent line increases. It's a high slope, or a very negative slope if the function is decreasing very quickly in that region. In places where the function is decreasing or increasing slowly, like where it flattens out here and here, the slope goes to 0. And here too. And up here. Watch. It's going to flatten out to a slope of 0 up, right up there. Briefly, that's what it did. We can define a function whose output is the slope of that line at different points. And it may seem like an impossible task to do. I want the y value of the function not to be the y value of the curve that's there, but to be the slope of the tangent line at that point on the curve, at all points along the curve. How on earth are we going to do that? Now, going back to the idea of something I briefly mentioned. If you take any curve and zoom in, and I'm going to try to bring Desmos back. Let's see, okay. So I'm going to bring Desmos in and pick a nice curve. Let's go not a straight line because that's boring. Let's go 6x to the power of 4 minus 3x cubed minus 30x cubed. No, too big. Minus 7. There, that's a little better. Minus 7x cubed. So there's a graph I want to look at. I'm going to zoom into it. Okay, and you can tell it's on a straight line, right? Not a straight line. Now what I'm going to do is I'm going to zoom in super tight somewhere. I'm going to zoom in here. I'm going to keep zooming in. I zoomed in very, very far. I zoomed in enough that if I asked, is this a straight line, you'd say, looks pretty straight to me. If you take a ruler to it, it's going to match up along the ruler. What this line is that we're seeing is what the tangent line would look like at that point if we were to zoom in. Not if we were to zoom in. That's what the tangent line would look like. It's the line that approximates the curve at a particular point. I just wanted to show you that because I mentioned that earlier and thought it's worth showing what I mean by what is the line that approximates the curve at a point. It's just the line that you would see if you zoom in close enough. Okay, so we saw that we can talk about average rates of change and then shrink down the x values over which we're calculating that average. Well, this limit definition just says shrink it down to nothing. Let the change in the x coordinate go to 0. Calculate an average rate of change over an infinitely small change in the x value, which we call h. We want the y value of the function. We want how much money is in the bank account at a plus h minus how much money is in the bank account at a. So that's our delta y. Divide by that tiny h. That's going to tell us how sensitive this function is at that coordinate. It'll give us that slope of that line. Now, how good was our company doing at that millisecond, at that microsecond, at that nanosecond? That's the information that is contained inside this idea. So this is just labeling those pieces, highlighting the top is the delta y, bottom is the delta x, and that the limit in front is what forces that change in the x value to get extremely small, infinitely small. Without the limit there, it's just an average rate of change. And again, we want to be able to recover this slope or this sensitivity, this average rate of change over a very small delta x. We want to be able to recover that for all x values. So in the previous expression, we had f prime of a, the derivative of the function at a, and all we're going to do is we're going to replace all the a's by x's, and that will actually give us that function that I said would be really hard to get. No, it's really easy to get, as long as we can calculate this limit. If we can calculate this limit, it'll give us the slope of that line at every point along the curve. Without having to make pictures, without having to make graphs, it'll give it to us almost for free. And I say that, and you're going to look at the calculations and you say, hey, that wasn't for free. That was hard to do. Now, before we launch into the calculations for calculating derivatives using this definition, I want to warn you about notation. Calculus developed over centuries with different personalities, different people leading different notations, many of which still survive. The f prime of x notation is a very popular notation. It's the one that we're primarily going to use inside this course. Y prime is an equivalent notation. The prime just means take the derivative. The ones underneath are also popular, and we're going to use those as well. They're probably the most accurate, they're the least misleading. dy by dx. That's like delta y over delta x. It's connected to that definition, the limit definition, the limit of the delta y over the delta x. So dy, difference in y, small change in y, over dx, difference in x. You could also say it's df by dx if the function is representing the y value, which it does. The last one there that's in that third line, d by dx of f of x, looks particularly strange. It's the operator notation. You're operating on the function with the derivative operation. So you can square a function or square root a function. Well, this is saying take the derivative of the function. So do this to the function. And there's other notations. These are the main survivors. I won't show you the ones that have basically not survived. Now, different textbooks and different resources call what we're about to do in these calculations different things. I'm going to call it the four-step process, even though it's not always going to be done in 4 steps. Sometimes it'll be done in 3 steps. Sometimes it'll be done in 2 steps. But I'm just, for the sake of consistency and for the sake of unambiguously identifying what you are expected to do, I'll call it the 4-step process, also called the definition of the derivative. So whenever you're asked to use the 4-step process or use the definition of the derivative to solve problems, you have to use this definition to find f prime of x. Limit as h approaches 0 of f of x plus h minus f of x all over h. I'll start the next video with an example for doing this type of a calculation.